Okay, hello everyone. Happy New Year. And I also wish may the whole world get a new beginning this year. Welcome to the 52nd and our first online Spintronics seminar of this year. It's my great pleasure to introduce our speaker today. Professor Kab-Jin Kim is a E1 Assistant Professor of Physics Department at KAIST, Korea, working on various fields in spintronics and magnetism. He received his PhD in physics from Seoul National University in 2011, advised by Professor Sakbong Choi. After that, he was a postdoc fellow in Professor Taro Ono's group. In 2013, he became an assistant professor in the same group and then moved to KAIST in 2016. Professor Kim has received many awards, including the Asian Union of Magnetic Society Young Researcher Award, T.J. Park Science Fellow by POSCO Foundation, and the E1 Assistant Professorship for Outstanding Junior Faculty at KAIST. So without further ado, Professor Kim, please go ahead with your talk.
Okay, thank you for kind introduction. Okay, good morning or good afternoon, everyone. So my name is Kab-Jin Kim, and I'm from KAIST in Korea. Okay, first of all, I'd like to thank Professor Fan and Professor Belashenko for organizing this wonderful online Spintronics seminar, and also give me a chance to introduce my research. Okay, so today my topic is the spin dynamics in ferrimagnet. Okay, so now we are studying the spintronics. I think the spintronics is composed of the spin transport and the spin dynamics. The spin transport is, for example, the spin-dependent electron scattering, but what we can call the spin dynamics is actually the magnetization dynamics. Okay, so if we apply the magnetic field, this single magnetic moment is start to precess and damped to the magnetic field direction. So this is the spin dynamics of the single magnetic moment. But in real materials, there are several magnetic structure, or someone calls the topological spin structures. For example, domain whirl or spin wave, skyrmion, or vortex. Okay. The reason why these spin structures are important is that we can make a device using those structures. For example, race-rank memory or vortex memory. And recently, people try to make a skyrmion the memory. Okay. So in these memories, we just use the dynamics of the spin structures. So we have to understand the spin dynamics. So now I'm talking about the dynamics, and every dynamics has a time scale, static or the slow dynamics or fast dynamics or ultra fast dynamics. Okay, and depending on this time scale, we can see the different physical phenomena. For example, thermal activation process, or the viscous flow, or precessional motion. So measurement technique also depends on the time scale. So for slow the dynamics, we can use both the electrical and optical technique, but for ultra fast dynamics, we have to use the optical technique. Okay. So here, I just plot the time scale in this vertical axis, and in the horizontal axis, I put some the driving mechanism. For example, field-driven, or spin transfer torque-driven, or spin orbit torque-driven. So we can find some research topic in every area in this region. And for example, you can do something in field-driven, slow dynamics, or the spin transfer torque-driven, fast dynamics, something like this. Okay, and so this is what I have done so far. Okay, so just for fun, so I just put some variation in these symbols. Here the size variations. The size depends on the general impact factor. This is just for fun. But you can also see the color here. So here the blue color means that the work that I have done when I was a student. And here the green color means that the work that I have done after getting PhD. So obviously, my research is now expanding to this direction. Okay, so I want to go to the ultra fast spin the dynamics. Then how to obtain the ultra fast spin dynamics? Okay, to do that, we have to look into the material. So we can plot another axis here, which is actually the material wise. Okay, so far most of the work have been done in ferromagnet. Okay, but to achieve the ultra fast dynamics, we have to go to the antiferromagnet, and this in between this antiferromagnet and the ferromagnet, we have a ferrimagnet. Okay. In the past few years, I have done some work on this ferrimagnet. And indeed, I could obtain the very fast spin dynamics in this ferrimagnet. So this is actually what I'm going to talk about today. Okay. Okay, so in recent years, we have seen the emerging of the new field named the antiferromagnetic spintronics. In fact, there are many review papers, which means that many people are now interested in antiferromagnet. The main motivation is that, as I mentioned, we can obtain the fast spin dynamics in antiferromagnet. Okay? Then why the antiferromagnet has such a fast spin dynamics? To understand it, we first have to figure out the key difference between the ferromagnet and antiferromagnet. Here I plot the schematics of the antiferromagnet and ferromagnet. So if we induce some torque to the system by magnetic field or the spin transfer torque, then in antiferromagnet, the neighboring the spin is just tilted. So you can see that their relative angle changes. So exchange energy change in this case. But in ferromagnet, if we apply the torque, all the magnetic moment tilt. So the relative angle does not change. So if we consider the energy, antiferromagnet, the exchange energy changes, but in ferromagnet, anisotropy energy changes. So if you consider the energy scale of the exchange energy and anisotropy energy, so exchange energy is much higher than the anisotropy energy. So this is the reason why we can see the fast dynamics in antiferromagnet. Okay. So we want to go to the antiferromagnet, but we also know that there are challenges to realize the really fast antiferromagnetic device. The most important and critical problem is that the antiferromagnet does not respond to the magnetic field. So it is extremely difficult to control and detect the antiferromagnetic spin dynamics. So here, my idea is that, what about the ferrimagnet? Okay. As all of you know, the ferrimagnet is microscopically antiferromagnet. Okay, because the neighboring spin aligned, directed to the opposite direction. But in macroscopic point of view, this is a ferromagnet because there is a net magnetic moment. So it responds to the magnetic field. So we can control it. Okay. So actually, in the nature, there are a number of the ferrimagnet, but here we focus on the rare earth transition metal ferrimagnet. So to make this ferrimagnet, we just mix the two material, rare earth and the transition metal. Then we can have the amorphous alloy. But interestingly, in this material, for example, if we mix the iron and gadolinium here, their magnetic moment directed to the opposite direction. Okay, so this is the ferrimagnet. Okay. The rare transition metal ferrimagnet has very special special temperature. So now we have two different magnetic moments. For example, here the rare earth and the transition metal, we just mixed. Okay, then they have different temperature characteristics. For example, if we plot the magnetization as a function of temperature, this is the red line, red curve is the magnetization of the rare earth, and this blue one is the transition metal. Okay, so they are oppositely directed, right? So if we sum up these two, the magnetic moment, then we can obtain the total magnetic moment. Then this is the total magnetic moment. So as you can see here, we have some point here where the total magnetic moment is 0. So this is the magnetization compensation point. Okay. But in this rare transition metal ferrimagnet, we have another compensation point named the angular momentum compensation point. Let me explain it. Okay, so basically, the magnetic moment and the angular momentum is proportional, and their ratio is this gamma is a gyromagnetic ratio. Okay. So gyromagnetic ratio determines the ratio between the angular momentum and magnetic moment. And if you look at this gyromagnetic ratio, there is a G factor here, okay, G factor. And now we just mix the two different material, and these two different material has different G factor. That means gyromagnetic ratio, their gyromagnetic ratio are different, okay? So the point where the total magnetic moment is zero is different from the point where the total angular momentum is zero. Okay, so the point where the total angular momentum is zero, in this point we call the angular momentum compensation point. So this is a schematic, and actually we can expect that this angular momentum compensation temperature is a little bit higher than the magnetization compensation temperature. So we have two compensation points, magnetic moment compensation point and angular momentum compensation point. Okay, then why this angular momentum compensation point is important? That is because now we are studying the dynamics. I'm studying the dynamics. Okay, dynamics is determined by the angular momentum, not the magnetic moment. Okay, so at this point, angular momentum compensation point, we can see the pure antiferromagnetic spin dynamics. Okay, because now the angular momentum is zero. Okay, but good thing is that at this point we have finite magnetic moment, so we can control it and we can detect it. Okay, so we have tested this idea. So this is the topic I'm going to talk about today. So I'll talk about the domain whirl. I'm going to show you the domain whirl motion in ferrimagnet and the spin wave in ferrimagnet. And if time allows, I'm going to show you some spin transport phenomena. For example, spin transport or magnetoresistance. But here, what I want to emphasize is that we could obtain the antiferromagnetic spin dynamics or transport in ferrimagnet. So this is what I want to emphasize. Okay, then let's start from the domain whirl. Okay, so to understand the antiferromagnetic domain whirl motion, ferrimagnetic domain whirl motion, we first have to understand the domain whirl motion in ferromagnet. Okay, so this is a very simple the picture. So in ferromagnet, if you apply the magnetic field, if you increase the magnetic field, then the velocity is linearly increased. We call this regime as a steady regime. So domain whirl moves just like this. But if we increase the magnetic field further and further, then this velocity abruptly decrease and then increase again. We call this regime as a precessional regime, and the domain whirl moves like this. Domain whirl shows some precession. So now the energy is divided into the translational motion and rotational motion. That's the reason that velocity is decreased. Okay, we call this phenomena as a Walker breakdown. Okay, and this Walker breakdown of the ferromagnet was beautifully demonstrated by the Professor Jeffrey Beach in 15 years ago in this paper. Okay, so this is the domain whirl dynamics in ferromagnet. Then, what about the antiferromagnet? What's the difference in the ferromagnet and antiferromagnet? In antiferromagnet, the situation is quite different because we don't have the angular momentum. Okay? The precession basically is coming from the angular momentum. So in antiferromagnet, we don't have total angular momentum. So in ferromagnet, we can see the precessional motion, but in antiferromagnet, there's no precession. Okay? So you can simply understand this like by using this spinning top. Okay, so we have spinning top here. So if top is spinning, if top is rotating, then this top is start to precess. But if there's no angular momentum, if this top is not spinning, then this top is just fall down. Okay, this is the key difference between the ferromagnetic domain of motion and antiferromagnetic domain of motion. In antiferromagnet, there's no angular momentum, so there's no precession, no Walker breakdown. So this work of breakdown is suppressed, can be suppressed in antiferromagnet. So we have checked this antiferromagnetic domain of motion in ferrimagnet. Okay. So our sample is a gadolinium ion cobalt, and the transition metal is ion cobalt, and here's the rare earth is gadolinium. So we made this sample, and we measured the field-driven domain of motion. But here, as I mentioned, the domain of motion, the speed is very fast. But generally, it's very difficult to measure the field-driven fast domain of motion, because when you apply the magnetic field to the system, there is always the rising time of the magnetic field, because if you make an electromagnet, there is always a rising time. So it's very difficult to measure the fast domain or field-driven domain of motion. So here, our idea is that we developed the real-time domain measurement technique. So we before the measuring, we apply the magnetic field. So this magnetic field is smaller than the coercive field, so nothing happened. And then we create the domainer by applying the current pulse here. Then the domainer is created. We already applied the magnetic field, so there's no rising time of the effect of the rising time. So the created domainer is moved to the right. Okay, and this domain motion is detected by measuring the whole resistance. So by using the oscilloscope, we can measure it in real time. Then we can obtain this kind of the data, and we can measure the domain travel time, and we know the distance, so we can determine the velocity of the domain. Okay, so using this technique, so we measure the domain velocity. So before measuring the domain velocity, we first define the magnetization compensation point. Okay, so it's easy. We just measure the whole resistance. Okay, this is anomalous the whole effect. So we measure the whole resistance in various temperature. And if you look at this low temperature, this hysteresis loop is clockwise, right? But in high temperature, hysteresis is anti-clockwise. That means the sign of the whole resistance changes at some temperature. Okay, and if you look at the coercive field, is increase and decrease. Okay, so we summarize here the coercive field and the whole resistance. So there is a sign change here, 220 Kelvin. So this is the magnetization compensation temperature. At this point, the coercive field is diverges. This is because now to switch the magnetization, we have to put some energy, and energy is Gman energy. So now at this point, magnetization is zero. So we need an infinite magnetic field. That's the reason why this coercive field is diverged here. So from these measurements, we can determine the angular momentum compensation point, magnetic moment compensation point. Okay, but finding the angular momentum compensation point is very difficult. Very difficult. So we just measure the domain of velocity. So the angular momentum compensation point, let me just say the TA. TA is expected to be a little bit higher than the TM, magnetization compensation point. So we just measure the domain of velocity above this compensation magnetization compensation temperature. So if you look at this this is the velocity as a function of magnetic field, and the domain velocity increase and decrease. So if we plot the domain velocity as a function of the temperature, then there is some maximum here, and this point we believe this is the angular momentum compensation point. At this point, domain dynamics becomes antiferromagnetic and very fast. Okay. So this is just expectation, okay? So we checked whether it is really the angular momentum compensation point or not. So by using some theory or the simulation, in this simulation, we just simulate the domain of velocity as a function of the total angular momentum here. So this simulation beautifully reproduced this experimental result. So if you look at this, we can obtain the maximum domain of velocity at zero angular momentum. That means this point is really the angular momentum compensation point. Okay, so that means now the work of breakdown is suppressed here. So at first there is the work breakdown, but as we approaching to the angular momentum compensation point, this work breakdown is suppressed and the domain velocity is increased. Okay, so that's what we observed. Okay, so the message from this domain of motion is that you can observe the pure antiferromagnetic spin dynamics at this point, angular momentum compensation point. And it is controllable by magnetic field. And this provides a way to determine the angular momentum compensation point, which was not easy so far. Okay, so this was the message. So now we are measuring the domain of velocity as a function of the magnetic field. So if you look at this equation, then if we obtain the slope of this domain of velocity, then we can determine the damping actually. So the domain of velocity measurement is one way to determine the damping of the system. Okay, so we checked the domain of velocity in the ferrimagnet, and we first defined the angular momentum compensation point here. Okay, and then we measure the domain of velocity, and if you look at this domain of velocity, the slope is increased as we approach the angular momentum compensation point, and then decreased. Okay, so if we use the ferromagnetic model, then you can see that this slope is proportional to the damping. Okay, proportional to the damping. That means that now the damping seems to increase at the angular momentum compensation point, right? But this is not true. This is not true because this model is a ferromagnetic model. So now we are studying the ferrimagnet, and in ferrimagnet we have to use the two sublattice model. Okay, so by using these two sublattice of the ferrimagnetic model, the damping is something like this. Okay, damping that does not depend on this angular momentum compensation point. There's no increase. So damping is almost constant. Okay, so we also check this by using the FMR, which is another conventional technique to obtain the magnetic damping. Okay, so FMR is the same. Okay, so if we here is the TA. Okay, if we approach the to the TA, so if we use the ferromagnetic model, then the damping increase. That means the line width of this FMR spectra increase at the TA. But if we use the ferrimagnetic model, then it's almost constant. So damping is almost constant here. Then you can tell that what is the difference between the two models. So now we have a ferromagnetic model and ferrimagnetic model. So what's the difference? Okay, so ferromagnetic model we have one sublattice, but ferrimagnet we have two sublattice. And this, if you look at this, this slope that depends on the total angular momentum. So at TA, this total angular momentum is 0. That's the reason why the slope increased. Okay, but well, I'm not actually so familiar with the theory. So here, let me explain the conceptually. Okay. So now we can understand the damping, magnetic damping, as that how fast the magnetic moment aligns to the magnetic field direction. Okay. So we can understand the damping like this. Okay. If there is the angular momentum, then this one is start to precess and damp to the magnetic field. Okay, but if there is no angular momentum, then this magnetic moment is just fall down. Okay, like this. If this top does not rotate, then it just fall down. Okay, so this is the reason why it seems to increase the damping. Okay, so now this top is fastly aligned to the magnetic field direction, because it just falls down without the precession. Okay, so the reason why the slope in the domain of velocity or the line width in the fMR spectra increased at the TA is not because of the increased damping, but because there is no angular momentum. If there's no angular momentum, no precession, so this magnetic moment is just aligned to the magnetic field. we just feel that, well, damping seems to be very large, but it's not. Damping is not increased at TA. Okay, so the message here is that the correct damping of ferrimagnet can be obtained by considering two sublattice model. And here the magnetic damping is almost independent of TA. Sorry, there's some technical problem. Is it okay? Sin is okay?
Yeah, yeah, I can say it now.
Okay, can I continue?
Yes, please.
Okay, okay. So here what we found is that magnetic damping is small. Magnetic damping is small in gadolinium ion cobalt. So now the damping, the value is smaller than the 0.01, very small and independent of the temperature. Okay, so this is the message. Okay, so then let's move on to the spin wave. What about the spin wave in ferrimagnet? Okay, the spin wave is coming from the spin precession. Okay, so let me start again by figuring out the crucial difference between the ferromagnet and the antiferromagnet. Okay, in ferromagnet, we only have the right-handed spin precession. Okay, because of the symmetry breaking. So we can, in this case, we can define the amplitude of the precession, amplitude and phase of the spin wave. But in antiferromagnet, we have left-handed mode as well as the right-handed mode. So we can define the amplitude, phase, and spin polarization. No, not just polarization. It's like a light. Okay, so if the light has a right, if we have the right handed and the left-handed mode, then if we mix these two modes, we have a linear polarization, right? So like this, we can define the polarization information in this antiferromagnet. So this is the key difference. In antiferromagnet, there are two modes, left-handed and right-handed. Okay, then what will happen in ferrimagnet? A little bit complicated because now we have two compensation points, magnetic moment compensation point here and angular momentum compensation point here. Let's say that we apply the magnetic field in this direction. Then at low temperature, let's say that here we mix the gadolinium and cobalt. Okay, then at low temperature, gadolinium moment is dominant. So gadolinium moment is aligned to the magnetic field direction. And angular momentum is opposite, right? So the gadolinium angular momentum is opposite and the cobalt angular momentum is opposite, like this. And very high temperature, in this case, cobalt is dominant, okay? Cobalt is dominant. So if we apply the magnetic field, cobalt aligns to the magnetic field direction and the angular momentum is opposite because the electron has a negative charge, okay? Then in between these two temperatures, in between these two temperatures, what will happen? Let's see. Okay, so now this temperature is above the magnetization compensation point. So in terms of the magnetization, now the cobalt is dominant. But still, this temperature is below the angular momentum compensation point. So in terms of the angular momentum, gadolinium is dominant here. Okay, then if we sum up all the magnetic moment and angular momentum, then it looks like this. This is total angular momentum. So if you look at this, low temperature and high temperature, magnetic moment and angular momentum directed to the opposite direction. That means the gyromagnetic ratio is positive here. But in between these two temperatures, magnetic moment and angular momentum aligns to the same direction. Okay, that means we have a negative gyromagnetic ratio. So what does it mean? If we have a negative gyromagnetic ratio, that means we have left-handed spin precession. Okay, so now we can control the spin wave from right-handed, left-handed, and right-handed by increasing the temperature. Okay, then what will happen in frequency? So if you change the temperature, at this point, angular momentum compensation point, the spin wave behaves like an antiferromagnet. So as I mentioned, at this point, two mode in antiferromagnet, two mode, left-handed and right-handed is just degenerated, and we can expect very high frequency here because it's an antiferromagnet. Okay, then if the temperature is above this the TA, then the cobalt angular momentum becomes rise. Then these two mode is splitted, and we have a low energy ephemeral mode, and we have a high energy exchange mode. And the low energy mode is right-handed, and high energy mode is left-handed. We have two modes. So if we decrease temperature, we know that between these two temperatures, the handedness is reversed. So in this case, we have left-handed mode and the lower energy mode with left-handed and higher energy mode with right-handed. And if the temperature is further below this magnetization compensation point, then in this case, magnetization is just flipped, and now this arrow is just flipped, and now this left-handed mode is converted to the right-handed mode. So simply, if we increase the temperature, the spin wave mode is changed from if we look at the lower energy mode, then changes from the right, left, and right. And the frequency decrease and increase and decrease. Okay. At this point, the magnetization compensation point, we have a minimum frequency because there's no magnetic moment, and there's no Zeeman coupling. Okay. So in this case, in this point, we can have the minimum, the frequency. Okay, so we just check this expectation experimentally, and in this case, we use a gadolinium cobalt ferrimagnet. Okay, and we use a Brillouin light scattering method to measure the spin wave. And here, so we measure the magnetostatic surface spin wave mode, and because the magnetic this spin wave is surface mode, so we can measure the localized at the top surface. We can measure the spin wave localized at the top surface. Okay, so because of this, we can have some asymmetry between the Stokes mode and anti-Stokes mode. Okay, so this is the result. First, let's see what happens if we increase the temperature across this magnetization compensation point. Okay, so this is the whole measurement. So now the sample is in plane anisotropy, and we apply the magnetic field to the perpendicular direction. So basically, we obtain the hard axis loop, but magnetic field is not enough, so not saturated. But anyway, here, sine, the slope changes in whole resistance. That means here, around the 360 Kelvin is the magnetization compensation point. Okay, so and this is the BLS result, and exactly at this point, we can see very interesting phenomenon. So now we can see some asymmetry between the Stokes and anti-Stokes in the amplitude, right? But this symmetry is reversed here. Okay, so Stokes, anti-Stokes, the relative intensity is reversed at this point. So that means now there is a gyromagnetic reversal, and the right-hand spin wave is reversed to the left-hand spin wave at this point. And if you look at the frequency here, frequency is decrease and again increase. Okay, so we summarize here the frequency decrease and increase. So indeed, we observe the minimum frequency at the magnetization compensation point because there's no Zeeman coupling in it here. Okay, then what will happen if we increase the temperature more? Okay, so now this is another sample. because our BLS measurement can be, the measurement temperature is from the 300 Kelvin to 420 Kelvin. And in the previous sample, the magnetization compensation point is around here. So we cannot measure the angular momentum compensation point here. So we used another sample, which has the angular momentum compensation around the 360 Kelvin here. And if you look at this BLS data, in this case, the frequency increase and decrease here. And the relative intensity also the changes from the positive to the negative like this. So that means this is the relative intensity, and this reversal means that again the spin wave mode change from the left-handed to right-handed. Okay, and at this point we obtained high frequency, and we also observed the two mode, the high energy mode, exchange mode, and the low energy ephemeral mode, and they are crossed at this point, angular momentum compensation point. And interestingly here, we observed some gap in opened. Okay, so these two modes should be crossed here, but we observed some gap here. So this is because the anisotropy. Okay, so at that point, the angular momentum compensation point, right-handed and left-handed is exactly degenerated. Okay, so we have linear polarization, but linear along the surface and the linear perpendicular to the surface has a different energy because there's a now finite magnetization, and there's some the demagnetizing effect. So because of this symmetric breaking, there is a gap here. Okay, but then now you can tell that you use the two different material, two different samples, right? So is it possible to obtain the TM and TA and the same sample? Yes, it is possible. Yeah, this is the result. So now the TM is around the 320 Kelvin and TA is around the 380 Kelvin. And if you look at this BLS spectra, then the Stokes anti-Stokes symmetry is changes again. Here is the reverse, and exactly we can see the high energy mode here. So if we summarize the result here, then you can see this, and this is actually what we expected. Okay, frequency is decreased and has a minimum at this magnetization compensation point, and then increased, and here's the two mode is crossed here. But what we observed is that there is a gap is opened. So this is coming from the anisotropy, the magnetic anisotropy. Okay, so we confirmed the spin wave in this ferrimagnet. Okay, and in addition to this, we observed very interesting phenomenon. So now the two mode, the low energy ephemeral mode and the high energy, simply the right-handed and left-hand mode is crossed. It's crossed at the angular momentum compensation point. Then you can think that this point is angular momentum compensation. Okay, but this is not actually, because this mode crossing point depends on the magnetic field. So if you increase the magnetic field, this mode crossing point is shifted. Okay, to check this, we developed the theory, and this theory actually was developed by Professor Segwon Kim, and I don't know the detail, but anyway, so if we solve these equations, then we can reproduce this. So if you increase the magnetic field, then this mode crossing point is shifted. So this can be easily understood, because let's say that we have an antiferromagnet here, like this. We have an antiferromagnet, and in this case, the right-handed mode and the left-handed mode is exactly the degenerate, right? But if we apply the magnetic field, we can break the symmetry. So the frequency of the right-handed and frequency of the left-handed can be splitted, even in antiferromagnet. So this is the reason why this mode crossing point depends on the external magnetic field. So that point is not exactly the angular momentum compensation point. So if you apply the magnetic field, this point is shifted. Okay. So the message of the spin wave is that you can see the antiferromagnetic spin wave at angular momentum compensation point. in ferrimagnet. And the handedness of the spin wave also can be controlled in ferrimagnet. You can control it right-handed and left-handed and right-handed. You can control it. Okay. Okay. Then how much time do I have? Okay. Then I will briefly introduce some transport region. Actually, this spin transport has been introduced theoretically by Professor Kab-Jin Lee in this online seminar. I remember last November. So let me just briefly explain the experiment and the key result. Okay, so question is simple. So now we have a ferrimagnetic domain world, right? So what happens if we flow the current instead of the magnetic field? So we just flow the current. Okay. To do that, we measure we prepare the sample, gadolinium, iron, cobalt, and we have a symmetric sample, so there's no spin orbit torque, and we just measure the field-driven domainal motion with bias current. So this is because we want to minimize the effect of the Joule heating. Okay, because now the ferrimagnet is crucially dependent on the temperature. Okay. So we first define the angular momentum compensation point here, and then we apply the current. And below these temperatures, the positive current assists the domainal motion, but above this temperature, now the positive current prevents the domainal motion. And even at the compensation point, there is a slight difference between the positive and negative current. So if we summarize the current induced the velocity shift, then this is what it looks like. Okay. Then we need the theory, right? I think the Professor Kab-Jin Lee already explained this. Okay, so now we flow the positive current and negative current, and the even effect is a field effect, and odd effect is a pure the current effect. Okay, odd effect can be explained by the adiabatic spin torque and non-adiabatic spin torque. Then how to distinguish the adiabatic spin torque and non-adiabatic spin torque? So if you look at this, adiabatic spin torque is anti-symmetric across the angular momentum compensation point. But non-adiabatic spin torque is a symmetric. So if we decompose the symmetric and anti-symmetric component, then we can obtain the adiabatic spin torque and non-adiabatic spin torque. So we have experimental data, and we decompose the symmetric component and anti-symmetric component. And from this, and we have experimental result, and we have an equation. Then we can fit the data, and we obtain the value, some value, and they have all the physics. Okay, so the message is damping is small. So this is very small. So this is consistent with the field-driven the mobility measurement, FMR measurement. Okay, and the non-adiabaticity is negative here. We don't know why. Anyway, it's negative and very large. And here's the ratio between non-adiabaticity and the damping is very large in this ferrimagnet we found. This is very important because in the current-driven domain motion, for the spin transport torque case, beta over alpha is the mobility. So if this value is large, then you can have very fast current-driven domain motion. Okay. And here's the importantly, the adiabatic spin torque is a uniform field, but non-adiabatic spin torque act like a staggered field. So you can drive the domain world even in angular momentum compensation point by using the non-adiabatic spin torque. So if you have antiferromagnet and there is a non-adiabatic spin torque, then you can drive the domain world, antiferromagnetic domain world. Okay. Okay, so lastly, let me briefly introduce the magnetoresistance. Okay, there are a number of magnetoresistance that exist in ferromagnet, right? Then my question is, what will happen in ferrimagnet? Okay, is the same or different? So the question is very simple. So in the transport in this ferrimagnet, which moment is dominant? This is my question. So now we have two moments, gadolinium and iron. Which moment is dominant for the transport? So this is my question. But actually, this rarest transition, the amorphous metal has been studying for a long time. So if you look at the very old paper, there was some debate. Okay, this is the long-standing problem. So in this paper, they said that the Hall effect is dominated by rare earths. Okay, but in some other papers, they said that the Hall effect is dominated by transition matter, not the rare earths. But in some paper, they said that the Hall effect is dominated by both. Okay, then what about now? Now we are studying the ferrimagnet intensively recently, and most of the people said that transition matter plays the dominant role in the transport of the ferrimagnet. That's because the 4f electron, which is responsible for the magnetism of rare earth, is much below than the Fermi level. So people just say that the transition matter is dominant. So I just want to check this experimentally, whether it is right or not. Okay, so again, we prepared the gadolinium ion cobalt here. At first, we measured the whole resistance and we defined the magnetization compensation point here. Okay, 160 Kelvin is the magnetization compensation point. And then we measured the longitudinal resistance. We just measured the sample resistance. Okay. So longitudinal resistance is almost constant in temperature, but if you apply the magnetic field, then we obtain some bow tie shape MR. Okay, and the sign changes at the compensation point, magnetization compensation point. At the below this temperature, the resistance increase if you apply the magnetic field, but above this temperature, resistance decrease. Okay. So at first, we suspect that the magnetic resistance can be the origin because this magnetic resistance shows a linear and non-saturating the magnetic resistance. But in this case, magnetic resistance, the slope increase at higher temperature because at higher temperature, there are more thermal magnons. So MMR increased. But our data shows that this slope decreased at higher temperature. So that means the observed MR is not coming from the magnon. There is another origin. Okay, so we thought that we think that it is coming from the ferrimagnetic nature of our ferrimagnet. Okay, so if we mix the iron and gadolinium, and they are spatially dispersed. And the iron and gadolinium has a weak exchange interaction. Because of this weak exchange interaction, they are not exactly the perfectly collinear. Okay? Their direction is a little bit dispersed, and they have some cone angle like this. Okay? So if we apply the magnetic field, we can expect that this cone angle changes. In this case, the iron cone angle increased, but the gadolinium cone angle is decreased. So if you apply magnetic field, then the cone angle changes. Then AMR, anisotropy magnetic resistance, can affect the longitudinal resistance because now their cone angle changes. Okay, but there is another problem. So if you look at, if we measure the AMR, actually this ferrimagnet AMR is very small, 0.1%. It's much smaller than that of ferromagnet, but anomalous Hall effect is very large in this sample. But if we apply the magnetic field, the variation is very large. The longitudinal resistance variation is 20% of the AMR, but Hall resistance variation is negligible. So anyway, now that we have a ferrimagnet, there is some cone angle, and if we apply the magnetic field, then the cone angle changes. But if the resistance is dominated by the only one the moment, for example, iron, then we cannot explain this. We cannot explain this because now AMR, the field variation, the longitudinal resistance changes very large, but anomalous Hall effect is negligible. So if but cone angle change should be reflected both in AMR and anomalous Hall effect because they have some angle dependence. So we cannot explain this. So to explain this, we have to consider both of the moment, gadolinium and iron. Then we can explain it. but this is a very theory. So let me just skip this and let me just explain the conceptually. So if you apply the magnetic field in this direction, gadolinium cone angle decrease and ion cone angle increase. So if you think about AMR, ion cone angle increase, so resistance increase. Okay, the gadolinium cone angle decreased, but gadolinium, the AMR coefficient is negative. So they are additive actually. The resistance variation is the changes are constructive. But if you think the whole anomalous Hall effect, then so now if you apply the magnetic field, all the magnetic moment can align to this magnetic field direction. But again, the coefficient of the gadolinium the anomalous Hall effect, this D is a negative, so they are destructive. So this is the reason. The AMR of the ferrimagnet is small, but field variation is very large. Anomalous Hall effect is very large, but field variation is very small. Seems very weird, but to explain this, here the point is to explain this, we have to consider both magnetic moment. So my question was which one is dominant in the transport? And the answer is both. Both magnetic moment contribute to the transport. So that means we can expect the antiferromagnetic spin transport. For example, the spin polarization compensation point, something like that, okay, in this material. Okay, so this is conclusion, and so this is just conclusion. So far as I have studied the spin dynamics in the ferromagnet, but recently in the past few years, I have done some work on the ferrimagnet, and indeed I obtained very fast spin dynamics, and that is actually the antiferromagnetic spin dynamics. So ferrimagnet is useful for spintronics. And before closing my talk, I have to thanks to my collaborators, Professor Segong Kim and Kab-Jin Lee. They just support the theory of all the experiment, and Professor Byung-Guk Park provided a wonderful sample to me. And my the former supervisor, Professor Teru Ono, he gave me a wonderful chance to study this ferrimagnet. And Dr. Chan Yong Hwang group at CRIS, they actually performed the BLS measurement, and Professor Sang Kim and Professor Chikamoto, they just provide me just amazing the samples. Okay, thank you.
Thank you very much for the nice talk. So this talk is open for questions. If you're in Zoom, please use the raise hand function. And if you cannot find that, you can always send me a private message. I will read the question for you. And if you're watching this on Twitch, please just type your question in the chat box, and I'll also read it for you. We have a first question by Gabriel Chavez. I'm just going to read the question to you. Doesn't the fluctuation dissipation theorem says the damping must be proportional to temperature? Would you be able to explain how this is still satisfied? And he was referring to the content in the between slides 28 and 30.
Okay. Yes, you're right. You're right. Okay, so damping should depend on the temperature, and here our temperature range is not actually wide. Okay, so we just measure the around the angular momentum compensation point, and what we want to show that is that the damping does not increase at this angular momentum compensation point. Okay, so now the temperature range is small. So if we expand this temperature range, we can expect that the damping should change it. Okay, so now the mechanism here is that we think that it's from the electron scattering at the Fermi level, and as you know, in this gadolinium ion cobalt at the Fermi level, ion cobalt is dominant because 4F is much below that the Fermi level. And if you look at the damping of ion cobalt is very small, almost the same. So we think that the gadolinium ion cobalt and the ion cobalt, their damping is the same. Yeah. So that's because the electron scattering at the Fermi level is important. Okay.
Thank you. So we have a second equation by Professor Matthias Clauy. I'm just going to read it. I think everyone can see that in Zoom. If the ferrimagnet has no temperature dependence of the damping, does that mean that the spin wave travel roughly the same distance at all temperatures and across the compensation points, assuming the same frequency of the magnets?
Of course, yes. Oh, yeah, of course, yes, because the damping does not depend on the temperature. But as I show you, the magnon, the frequency changes across the temperature. So if you consider the frequency, then yeah. But as you mentioned, assuming the same frequency, then it should be same.
Yeah. Can I have one quick follow-up on that?
Okay.
Yeah. So if you replace gadolinium, which is L equals 0, by a rare earth that has finite orbital angular momentum, would then the damping be much larger? Do you expect that to be much larger? Is gadolinium special, or do you think it's not?
Sorry, so I couldn't capture your point.
So if you go to terbium ion cobalt instead of gadolinium,
terbium ion cobalt, yeah.
Do you think the damping will be much higher because terbium has finite orbital angular momentum, like not L equals 0?
Yeah, but I'm not sure because the orbital angular momentum is coming from the 4f electron. Okay, so the 4f electron is much below that than the Fermi level, and we think that now the damping is coming from the electron scattering at the Fermi level. So even if you use the terbiums, but the damping can be determined by the transition matter, I think.
Okay, so still low. Okay, great.
Still
Thanks.
low, yeah. But I'm not sure. We have to check because we are experimentalists, right? So we have to check.
Absolutely.
Yeah.
Yes. Thanks.
Thank you. We have another question from Oksana. I'm just going to read it to you. Many works consider that magnetization and the angular momentum compensation points are close. This was because the gyromagnetic ratio are about just 5 to 8% different between the rare earths and the transition metal. How do you explain that you can get almost 80 Kelvin of difference in the TA and the TM in gadolinium ion cobalt?
Yes, yeah. Basically, I think you are right, and I cannot explain the quantitatively, but now the difference, temperature difference, is coming from the G factor difference, and the gadolinium, the G factor is 2.0, and the ion cobalt is the G factor is 2.2. The reported value is 2.2. So now the G factor difference is 0.2. That actually gives the temperature difference of around the 100 Kelvin. So actually there was some paper, the relation between the angular momentum and magnetization compensation point, and they can excellently explain it by using this G factor difference. Yeah, I think.
Okay, thank you. Let me see if there's another question on Zoom and on Twitch. Okay, it doesn't look like we have any more question at this moment. We'll have another discussion, off-the-record discussion afterwards. For now, I just want to thank the speaker again, and I want to thank all of you for participating.